And thank you, Ganguly sir, for inviting me to this FDP course, and welcome all participants. We'll today talk about the eclipses and transits mainly. Mainly, I will be talking about eclipses and the various different kind of calculations. I hope I am audible.
Yeah, you are audible.
Yeah. So, uh, what we shall do is, I mean, this is the general plan which is given to you, and I'll be talking about it. Though I may not talk more on occultations, I will later share the work done by one of my friends, Mr. Shishir Deshmukh, who is actively involved in the project of I mean, studying various kinds of occultations. So I will share that material later, but we'll talk about the eclipse calculations, some how some of the projects and things can be done, observations can be done, and we'll also talk about the transit. Though it is a rare phenomena, there are things that are very interesting as far as calculations are concerned. So first thing is we talk about moon takes, we know, 27 days for a revolution, while the month is 30 days long. And we all have this idea about the basic idea about astronomy, but some of the things will be a small quick revision. I hope that should be helpful to people. So here, just a drawing of the sun, and there is an earth over here. This is not obviously not to the scale, okay, but we are going to bother about the angular measurements. And on full moon day, the moon will be, suppose at one particular full moon day, the moon is at this particular point. Now, in that case, after 27.33 days or one complete revolution of the moon around the earth, okay, the moon will be, with respect to earth, will be in the same orientation. But now you see that it is not exactly opposite, and in about 27.3 days, the earth is also rotated around the sun by the same amount. Okay, and let me just keep my video off so bandwidth will improve. And 27 degrees angle earth would have made around the sun, and naturally moon should further travel by this much angle so that it becomes a full moon day. And for that purpose, it takes about more than 2 days, and therefore we say the next full moon is going to happen after 29.5 days, and that is what we call lunar month. Now these calculations can be done more precisely. So let's look at some of these calculations, and let's look at how it is directly affecting the eclipses. So first question then comes is, why do eclipses not take place every month? So that's because lunar orbit makes about 5.1 degree angle with the ecliptic. Ecliptic is the plane in which Earth is going around the sun, or with respect to Earth, I mean, taking Earth as a reference, we will see the sun moving around the Earth. Apparently, sun will be moving around Earth. So that plane is called ecliptic. And moon's orbit around the Earth makes about 5.1 degrees with that. Now, if the moon is on that intersection, okay, or is very close to that intersection, then it will be close to the ecliptic. And then we can see over here, in this case, the Earth shadow. The moon can come completely in the earth shadow, and the lunar eclipse can take place. Similarly, when moon comes between earth and sun, it can obstruct the sun and the solar eclipse will take place. And this can happen when the moon is at those intersection points called nodes, either on this side or on this side. But maybe after 3 months or so, the moon will be north of ecliptic, or it could be south of ecliptic. Now the shadow of the earth is always going to be in the ecliptic. By definition, sun is always on the ecliptic, and earth is also always on the ecliptic, and therefore the shadow of the earth is always going to be on the ecliptic. But if moon is north, okay, or north of the ecliptic, then in that case the moon shadow will of course go parallel like this, and when if it is new moon day, the moon shadow will go like this, and then it is going to miss the earth. It misses the earth by something like 33,000 kilometers, okay, and therefore and you know the diameter of the earth is about 13,000 kilometers. So when the position of the moon is shifted by something like 33,000 kilometers, when you do calculation of 5.1 degree, and you know the distance of the moon from the earth is about 3,84,000 kilometers. So you can find out that when it is farthest away from the ecliptic, okay, at what distance it could be. And then it turns out that we miss the eclipse. So eclipse do not happen every full moon day, new moon day. Of course, the solar eclipse will always happen on new moon day. That is because the moon will be coming between Earth and Sun, and the solar eclipse on new moon day. Therefore, the moon has same longitude as the Sun's longitude. Okay. Whereas on full moon day, the moon's longitude is 180 degree away from Sun's longitude, and therefore, on full moon day, you will always have lunar eclipse. The lunar eclipse will always happen on full moon day. So solar eclipse happens on new moon day, lunar eclipse happens on full moon day. This is basic information that one studies in astronomy. But when we go for further calculations, we realize that why every full moon day or every new moon day the eclipse do not take place. That's because the shadow orientation, the shadow directions change. And some of these calculations can be done. So what we know for sure, therefore, is that eclipses will take place only when the moon and sun will be along the line of node. So this is called line of node. What is line of node? So if you consider the moon's orbit around the Earth's orbit or around the ecliptic, there will be one particular point as moon is going around the Earth. Okay, it will cross the ecliptic and come to the north. That is called ascending node. There will be another point exactly 180 degree opposite, where the moon's orbit will cut again ecliptic, and moon will, as it is traveling in the anti-clockwise direction as seen from north, the moon will cross the ecliptic and from north to south. That is called descending node. As far as the ancient Indian astronomy is concerned, these points were called Rahu and Ketu. So many of you might be familiar with this. So ascending node is also called Rahu, the descending node is also called Ketu, and therefore there is direct connection between the eclipses and Rahu or Ketu points. We will see these, but we will refer always them in our lecture as per the modern calculations of astronomy as ascending nodes and descending nodes. So it is necessary, therefore, that the full moon or new moon should take place near the ascending or descending node. Only then eclipse will take place. Otherwise, eclipse will not take place. Now there are ecliptic seasons. So you can see from this particular figure that this is the plane of the Earth's orbit, okay, and this is the plane of the moon's orbit, okay, and this is the line of node where they are intersecting. Now here, if new moon day, the moon is coming between Earth and Sun, so the new moon days are going to happen somewhere over here. Here there is no eclipse happening. Okay, here it is just missing, and within this particular limit, any time if new moon day takes place around this node, okay, there is going to be solar eclipse. Similarly, there will be particular limit, okay, within which if the full moon day happens, okay, then you will see that the lunar eclipse takes place. Now look at these dates. So in the last year and this year, 25th, 26th May 2021 lunar eclipse was there. The two dates are given there because during that lunar eclipse period, okay, some region of the Earth may have 25th May, some region may have 26th May. Okay, so if it is typically going to happen around the international date line, then you will have two dates like this. Okay, 10th June there was solar eclipse, annular solar eclipse. 18th, 19th November 21 there was lunar eclipse, it was partial lunar eclipse. 4th December it was total solar eclipse. 30th April it was partial solar eclipse. 15th, 16th May it was total lunar eclipse. 25th October it is going to be 15th, 16th May it will be total lunar eclipse. 25th October it will be solar eclipse partial. 7th or 8th November again it is going to be total lunar eclipse. Now what you observe here is in May, June the eclipse is taking place. November, December eclipse is taking place. Again in April, May the eclipse is taking place. And October, November the eclipse is taking place. It is not taking place in between. So effectively, every 6 months, but it is not even exactly 6 months. What you observe here is initially it was May, June, later it became April, May, then it is going to further become somewhere around March, April. So though eclipses are going to take place in certain regions, certain months, and then after 6 months, okay, it seems that this entire cycle is slowly shifting. So this particular part, that May June eclipse was taking place and November December eclipse is taking place, this is called eclipse season. So eclipse season is when the sun is near any of the nodes, then it is called eclipse season. Now we need to consider how close it should be so that eclipse will take place, because we are only saying that the sun should be near the node, but how much near the node? Okay, it should be close to the node, but how close is close? Okay, we need to bother about the magnitude, we need to bother about the angular measurements. So let us come to that. And at any point of time, you have any question, something is not very clear, do ask. You can unmute and ask, or you can also put question in the chat. So we come to first question, which is more frequent, solar eclipse or lunar eclipse. Now, if you have any time observed solar eclipse or lunar eclipse, okay, generally sitting at one particular location, we know that typically in one's lifetime, one may have seen more lunar eclipses than solar eclipse. If you decide that every eclipse that is visible from your location you are going to watch, then naturally you find that more lunar eclipses will be, some particular person will be seen. That's because if the moon is visible and if moon is in the earth shadow, anybody who is going to observe the moon will see the lunar eclipse. However, that is not the case with solar eclipse. Solar eclipse, in case of solar eclipse, what happens? The moon shadow falls on the earth and it's a narrow band of about 200 kilometers. And then as the time progresses, this shadow is going to shift, and therefore people at different locations will be able to see the eclipse at different amount of time. But it is still restricted to small region, okay, and even if you consider the partial solar eclipse, okay, it is restricted in a particular time, okay, and therefore it may not be possible for everyone to observe the solar eclipse. In fact, in the last least, okay, not all solar eclipses, there are so many solar eclipses you see, not all solar eclipses are visible from India. Okay, sometimes the eclipse might be visible from the western part of India, but it may not be visible in the eastern part. Sometimes it may just start at the eastern part of India, but it may not be visible in the western part of India. So these kind of differences will take place. So the question is which is more frequent, and answer is, when you look at all the list of entire solar eclipses, it turns out that the solar eclipses are more frequent than lunar eclipses. And a simple geometrical diagram can help us to understand why so. So let's come to this. This is sun, this is again not to the scale. This is the earth, this is the moon's orbit, okay, and you see here this particular arc, okay, in this particular arc, anytime moon comes, it is going to be solar eclipse. In this particular arc, if moon comes, it is going to be lunar eclipse. You see this arc is larger, so there is more probability that solar eclipse will take place. This arc is smaller, there is less probability that lunar eclipse will take place. So just by this simple diagram, we can see that why solar eclipses are going to be more frequent than lunar eclipses. Okay, so let's come to make some calculations of this. Okay, so first we find out, you draw a proper geometrical figure, okay, and then there are various points I have noted down. So O is the center of the sun, O dash, this particular circle is the earth circle, this is the moon's orbit. Remember, it's not to the scale, okay, because drawing astronomical figures drawing to the scale of size is at times difficult. So what we are going to do is we are going to look at the angles, and these angles we will actually calculate precisely by putting the correct numbers. Okay, because we know that Moon's orbit is actually the radius of the Moon's orbit is 60 times the radius of the Earth. Okay, so showing all that in to the scale diagram is not going to be realistic on a small screen like this. Okay, so let's assume this, and we are going to put the numbers correctly while doing calculations. Okay, so this angle beta, which angle beta? So from this line joining OE, and this is basically the shadow of the Earth. Okay, and the length of the shadow of the Earth goes from E to C. So if you consider this line of OEC, okay, it is line joining centers of Earth and Sun. Now from this point to this point, wherever the Moon's orbit cuts this tangent to the Sun and Earth, okay, that angle is angle beta, and on the opposite side, this angle is angle alpha. Okay, so alpha and beta we need to do calculation. So alpha is this part, beta is this part, and alpha is calculated here as 41 arc minutes, and beta is calculated as 73 arc minutes. But we'll see the exact calculations. So now let us calculate alpha and beta. That will tell us which is more frequent and how it is more frequent. How frequent is the solar eclipse? So radius of the Sun. I mean, all these data are taken from Wikipedia here. Okay, the factual data here. The radius of the Sun is 696,342 kilometers. Earth Sun distance is 149598023 kilometers. This is one astronomical unit we call. Radius of the Earth, and this radius of the Earth is 6,371 kilometers. Earth Moon distance. Okay, I am taking an average distance over here. The average distance I am talking about. The values, actual values may slightly change because Earth's orbit around the Moon and Moon's orbit around the Earth's orbit around the Sun and Moon's orbit around the Earth are eccentric. The eccentricity for Earth's orbit is quite small, 0.016, but for Moon's orbit it is quite larger, 0.055, and therefore the Moon can come much closer and go much farther away from the Earth. But we'll first do calculation for the average distance. In reality, in certain conditions, the eclipses are going to be more favorable. In some other conditions, eclipses will be less favorable. Okay. So now let us do some calculation. So sin S, where S is the angle. Let me go back to the earlier slide. Was R of Sun, radius of the Sun upon distance of the Sun. Okay, and S turns out to be then, this is nothing but angular size of the Sun, 16 arc minutes. Okay, 16 arc minutes plus 0.12 arc second. This is for the average. Okay, so S is the angular size of the Sun, and angular size of the Sun is going to play an important role because there is a parameter called magnitude of the eclipse, which depends on the angular size of the Sun and angular size of the Moon. Now here we have got other relations. So let me just go back to the slide. Look at this particular formula. OC upon EC is OO dash upon EE dash. Let me go back to the earlier formula. So OC is this upon EC is OO dash upon EE dash. So what we have done is we have taken this triangle O dash EC and E dash EC, and these two are similar triangles. So using the property of similar triangles, we are saying that, and these are the congruent side, the corresponding side. Okay, so OC is corresponding to EC, O dash E dash is corresponding to OE, okay, and E dash C is corresponding to EC, EE dash is corresponding to OO dash. So considering this triangle and the smaller triangle over here, what we can do is we can write certain formulas. So OO dash upon EE dash is equal to OE upon EC. Now based on this, we can write further algebra. So let me do that. So OC upon EC is O dash upon EE dash. Then you do this algebraic manipulation, component those and dividend. Okay, and then ultimately what we get, OC minus EC turns out to be upon OC minus EC upon EC is O dash minus E dash upon E dash. Okay, and OC minus EC is basically radius of the sun minus radius of the earth upon EC is radius of the earth, and OO dash minus EE dash turns out to be the distance to the sun, because that and upon EE dash we are talking about. Okay, so let me just quickly refer OC, EC. What are these? These are OC is the total distance. EC is the distance from Earth to this tip of the shadow. Okay, so OC minus EC will give you the distance of the Earth to the Sun. Okay, and similarly, OC minus EC gives you distance to the Sun. OO dash is radius of the Sun, EE dash is radius of the Earth, and EE dash here is radius of the Earth. Okay, and EC is the shadow length. So we get this particular formula. I had slightly messed up earlier while talking about, but referring to the diagram, this presentation will be shared with you. Okay, referring to the diagram, okay, you can do these calculations. Now we have these numbers over here. So when you substitute these numbers, what you get is the shadow length. Earth's shadow length is 1381346 kilometers. So basically 13 lakh 81,346 kilometers. Because it is 13 lakh kilometer, okay, and the moon is at about 3 lakh 84,000 or 4 lakh kilometers. We know for sure that moon is always going to come inside the shadow if it is not far away from ecliptic to the north or to the south. Okay, so shadow length is one important calculation. And now, what is the angular size of the moon? The angular size of the moon is radius of the moon upon distance of the moon from the earth. And this is again I have taken average distance. So average angular size is 15 minutes 32.65 seconds. What you observe clearly here that the average angular size of the sun is going to be larger than angular size of the moon, and therefore what happens is there are going to be more annular eclipses than the solar eclipses, because in general the angular size of the moon is slightly smaller than angular size of the sun. So even when the centers of the moon and centers of the sun coincide, okay, the moon is going to fit inside the sun and the outer limb of the sun will be visible. And when outer limb of the sun is going to be visible, okay, what will happen is it is going to be annular eclipse. However, because moon can come closer to the earth and the eccentricity is high, what is possible is moon's distance can go down to 3,62,000 kilometers, and then this angular size of the moon increases and it can become greater than angular size of the sun. The angular size of the sun also changes when it is at perigee position or apogee position. I'm saying sun is at perigee position, basically earth is at perigee position that time, okay, around 3rd of January or so, and that time the size of the sun will also slightly increase. But because the eccentricity of the moon is much larger than eccentricity of the sun, okay, when moon is at perigee, its angular size is even larger than, typically larger than the size of the sun, and in that case the total solar eclipse is possible. So we have total solar eclipse possible because of angular size of the moon being greater than angular size of the sun at certain times. We continue our calculations further. So now here we are talking about sin theta, and what is sin theta? Sin theta is this angle theta. Okay, so sin theta is O dash C O, okay, or E dash C E. That is the half angle of the cone of that shadow, and that we can calculate, okay, as 6371, which is the radius of the earth upon the shadow length, and that angle theta turns out to be 15 arc minute 51.33 arc second. Now we have this other thing, P is equal to S minus theta. Okay, so let us look at what is P is equal to S minus theta. What is P, what is S, what is theta? Let us quickly come back. So P is this angle, E dash O dash E. Okay, S is O dash E O, and theta is this angle. So you see, if I consider a particular triangle, say O dash, C and E. If I consider this particular triangle, okay, angle S is an exterior angle, and therefore it will add to the other two angles, okay, P and theta. So S is equal to P plus theta. That gives us P is equal to S minus theta. S is equal to P plus theta. So P is equal to S minus theta. We have calculated the value of S. We have calculated the value of theta over here. That gives us value of P. Okay, it is approximately 8.8 arc seconds. Now this 8.8 arc second, okay, is also called as the equatorial parallax of the sun. See, if you look at the sun from the center of the earth, and if you look at the sun from the surface of the earth along the equator, because we have taken the equatorial radius of the earth, okay, there is going to be small parallax, okay, and that angle is about 8.8 arc seconds. It becomes useful for further calculation. This small parallax of the sun becomes useful when we are going to do further calculation. So let us come to that. Angle alpha, we already saw that is angle E dash PE minus theta. Let us see that E dash PE minus theta. So what is E dash PE? E dash PE. So E dash, if I consider this is the right angle triangle, so E dash PE, okay, minus theta. If I take, that will give me angle alpha. Why? Because let us take this particular triangle P, E and C. If I take triangle P, E and C, here what is happening is this angle theta plus this angle theta, okay, will give me this particular angle. But this angle is nothing but alpha, angle alpha. So this alpha and theta, okay, will add up to give you this exterior angle E dash PE, and that is what is written here. E dash PE is alpha plus theta, or alpha is equal to E dash PE minus theta. Now let us write this angle. So E dash PE is sine inverse of E dash upon EP. We are using we are using the property that is right angle triangle. Okay, let me go back to this and E dash PE. I am interested in sine of this. So what is sine of this angle? Okay, it is E dash E and EP. But what is E dash E? E dash E is nothing but radius of the earth. What is EP? It is nothing but the earth moon distance. Okay, radius of the moon's orbit. So sine inverse of radius of the earth upon the distance between earth moon or moon's orbit. Okay, that will give you this particular angle E dash PE, and let's calculate that. So we get 56 minutes 58.77 arc second. Substitute this along with theta, subtract this theta, which is 15 arc minutes, this is 56 arc minutes, and you get angle alpha as 41 arc minutes 7.44 seconds. So point is, it is a simple geometry. Okay, so when you actually sit with the diagram, the actual diagram and the numbers, the relevant data, you can calculate this. Okay. Similarly, we will have to calculate angle beta also. So this is angle alpha. For angle beta, we have to consider angle EMC plus theta. What is EMC plus theta? Let us go back. So E, M and C we are talking about. So this particular angle. So this particular angle plus this angle is also theta because this is symmetric. Okay, so this angle plus this angle will add up to give you this angle. It is exterior angle property. Okay, but this angle is nothing but angle beta. Okay, and therefore what we can do is we first need to calculate how much is this angle EMC, and again we can do that by the same formula, because E, suppose I put a E double dash over here. So E double dash upon this will give you sine of this angle. okay, and which is same as going to be this particular angle, okay, because it is the Earth's radius and Earth Moon distance, that ratio you are putting. So taking that, taking that into account, what we get is EMP is same as E dash PE, which is the ratio of the Earth's radius to Earth Moon distance, and therefore it is going to be 56 arc minute 58.77 arc seconds. Many times some of these significant digits may not be important, but for intermediate calculations I have put them. How many significant digits, up to how many decimal places you can write the answer. So we stick to some rule of significant digits. That if radius of the Earth is given up to 4 significant digits, okay, even if the Earth Moon distance is given with greater significant digit, the final answer is correct only up to 4 significant digits. So 56 minute and 59 hour second, I can round off like that. Okay, but for certain intermediate calculations, I have put extra decimal places. We need to, whenever you are going to do such kind of calculation, you need to always think about what are the significant digits in the calculation. Okay, because calculator can give you large values, but whenever you are taking differences within a particular ratio, you are taking a differences, then you have to see that the difference is correct up to how many significant digits. Okay, and then angle, accordingly the angles or other measurements one can write up to correct significant digits. So here beta turns out to be 56 minutes 58.77 hour second plus 15 minutes 51.33 hour second, and that is final answer is 72 minutes and 50 hour second, which you can round off to 73 hour minutes, or 4 significant digits are correct, so you may write 72 hour minutes and 50 hour seconds. That is going to be the value of beta. So these two values are important. This tells you the probability of lunar eclipses, this tells you probability of solar eclipses. This ratio 72 minutes 50 hour second upon 41 minutes 7.44 hour second, this ratio will clearly give you also the ratio of solar eclipses to lunar eclipses. Okay, so that's about you can always calculate. It is for example, I may consider this is 7:4. Effectively, this is like 7:4 ratio. Okay, and you may simplify it further, and you may bring it down to closer, smaller integer ratios also. Okay, but apparently directly you see something like this. You may say that this is almost double, but not exactly double of this. Yeah. Anything? Okay.
No, you can continue. Nothing.
Yeah. Now we talk about the ecliptic limits. So what are the ecliptic limits? Within how much angle moon or sun should be from the node on a full moon or new moon day to ensure eclipse is called ecliptic limit. We have already seen that not every full moon day or new moon day the eclipse is going to take place. Only if the sun is near the node and it happens to be a new moon day or a full moon day, then eclipse will take place. But now the question is, close to the node means how close is that close? Okay, how much closer it should come? So that is what we will be calculating here. So let's calculate first ecliptic limit for solar eclipse. So now here what I have drawn is an ecliptic, and then I have drawn here a circle which shows that it is the sun's cone at the moon's orbit. Now you see what is sun's cone at the moon's orbit. Let me come back to the earlier slide. This is the sun. Okay, the sun is forming a cone when you put a tangent with respect to Earth. So this is solar cone, and at moon's distance, this is the moon's distance. At moon's distance, how much is the extension? So how much is the linear extension of the sun's cone at the moon's distance? That is what we need to calculate. And that angular calculation we have done. Okay, that angular calculation we have done, which is nothing but angle beta. Okay, for if we are talking about solar eclipse, so it is angle beta. So it is sun's cone at the moon's orbit that subtends angle beta. Okay, at the center of the Earth. Now this is the limiting case. This is the moon's orbit, and the moon is going to move on that. This is the ecliptic. So Earth is the sun is always going to be on the ecliptic. This is the moon's orbit. Moon is going to move on that. Okay, but at the limiting case, the moon may just touch the sun's limb, at the external edge. So when it is just going to touch, that you have just missed the solar eclipse. Okay. If the sun is going to be inside, the moon is also going to be inside, because the longitude will be same on the new moon day. This circle and this circle will overlap. Okay, the two circles will overlap and solar eclipse will take place. So part of the sun will be blocked and we'll call it solar eclipse. We are not talking about the total solar eclipse, we are talking about any solar eclipse. As long as partial solar eclipse is taking place or full solar eclipse is taking place, we don't right now here. Okay, what is the ecliptic limit for solar eclipse? Why it is called ecliptic limit? Because on the ecliptic, up to what limit sun is allowed to be, okay, from the node, this is the node's position, okay, from the node at what maximum distance sun is allowed on a new moon day, so that eclipse will take place. That is what we are interested in. This angle is 5.1 degree, okay. For approximation I have written 5 degrees, but you can write more precisely as 5.1 degree. Let me change that here itself. And this is what we are going to calculate as ecliptic limit. Now we know this sun's cone and the moon's orbit we have calculated at 72 minutes 50 seconds, that is beta angle. And the angular size of the moon, what is the average angular size of the moon? So it is about 15 arc minutes, 32.65 arc seconds. This is what we have calculated. So this total angle is the addition of the two approximately, and if you divide by this sine of 5.1 degree, you get answer about 16 degree 54 minutes as the ecliptic limit. So ecliptic limit, this side, remember every side is in angle over here. Okay, so this is angular side, this is also angular side, and we know that sine of 5.1 degree is this side upon this side. Okay, so this side is nothing but this angle divided by sine of 5.1 degree, and because it is small angle, pi degree is a relatively small angle, you can convert angle into radians and directly use angle instead of calling it sine phi, because sine of theta is approximately theta in radians if the angles are small. So you may also convert 5.1 degree into radians, and you may write that, and you get answer something like 16 degree 54 minutes. This is the ecliptic limit. We'll see the interpretation of that. What is meant by 16 degree 54 minutes when it comes to number of days? We know approximately sun moves 1 degree per day, because it takes it completes 360 degrees around the earth in 365 days. I am talking about the relative motion. Okay, in kinematics it doesn't make a difference whether I say sun is moving around the earth or earth is moving around the sun. In dynamics it makes a difference. In kinematics it doesn't make a difference. So I may say that sun takes 365 days to complete 360 degrees, and therefore approximately 1 degree. So which means around 16 days are available beyond the node on one side as well as on the other side. So total of something like 33 days are available. Okay, within that 33 days, if new moon day happens, then eclipse will take place. And we know that new moon can surely happen within 33 days, because the lunar month is 29.5 days long. So because lunar month is 29.5 days long, it is surely every node when the sun is going to come closer, one eclipse will surely take place. We will see those calculations in slightly greater detail later on the slides. Let's calculate ecliptic limit for lunar eclipse. So again here what you have shown, ecliptic is shown, but now you are looking in the opposite direction. You are not looking at the sun, you are looking at the Earth's shadow region. How much is the size of the Earth's shadow when at the distance of moon's orbit? Let's go back to our earlier slide. We see here that this is the Earth's shadow. and this is the moon's orbit. So we want to find out how much is this size, okay, at the center of the earth. So how much angle the earth shadow is going to sustain, the earth shadow at moon's distance is going to sustain at the center of the earth. Remember, this is an exaggerated figure, though we are going to stand over here. The angle measured at the surface of the earth and angle measured at the center of the earth are not going to change much. The reason is the actual moon's orbit is something like 60 times greater than the earth's radius. Okay, so let's come back to our present slide. This is again the moon's orbit, and moon is going to be on the moon's orbit, and we know size of the angular size of the moon. Okay, this size we have calculated as alpha already. This is the moon size. This is going to be the node over here. Again, we are going to make 5.1 degree angle. Okay, and what we can do is we want to find out what is the ecliptic limit, but in this case we are not taking sun, we are taking earth shadow. So we are calculating ecliptic limit for lunar eclipse, and this angle alpha we have calculated already, that 41 hours minute 7.44 hours second. The size of the moon also we have calculated 15. This is the average size of the moon. At perigee, the angular size of the moon will further increase. Okay, and but those will go under favorable conditions. So I will talk about that in the next slide. Okay, so what is going to be the average ecliptic limit? So again, this angle plus this angle will give you this total side. This total side divided by sine of 5.1 degree will give you this particular side, which is 10 degree 15 minutes. What does that tell you? That when the sun is within the ecliptic limit of 10 degree 50 minutes, and if it is full moon day, okay, what will happen is the solar eclipse, the lunar eclipse will take place. So on each side it is 10 degree 50 minutes, approximately 11 degrees. So and sun is going to take about 1 degree per day. So we have got 11 degrees and 11 degrees, 22 degrees region available around the node. But there is no guarantee within that 22 degrees the sun, the full moon will happen. Because we know one full moon day to next full moon day will take 29.5 days. So it may so happen that just before entering the ecliptic limit, the full moon day occurred. Now, after that it is going to enter the ecliptic limit. 22 days it is going to be inside the ecliptic limit. The sun is going to be inside the ecliptic limit. Okay, but after leaving the ecliptic limit, the next full moon day will happen. Because full moon day has happened before entering ecliptic limit. One full moon day to next full moon day is 29.5 days. Okay, and sun is going to remain within this ecliptic limit only for about 22 days. So it is not necessary that every node, when the sun comes, the lunar eclipse will happen. Not necessary. But at every node, when the sun comes, solar eclipse surely happens. So in every year, therefore, we can say that minimum 2 solar eclipses must happen. So let's now consider unfavorable conditions and most favorable conditions. What happens? These ecliptic limits. Here is the node. This is the limit on the lunar ecliptic limit, and this is the limit on the solar eclipse ecliptic limit. So solar eclipse ecliptic limit we calculated about 16 degrees, okay, and something 15 minutes or so. And under unfavorable condition, okay, when the size of moon is smaller, okay, because moon is at apogee, okay, the angle will reduce. Okay, also the size of the sun's limb or size of the sun at the distance of moon's orbit, okay, or size of the sun's cone at the distance of moon orbit, that can reduce, okay, because Earth's orbit around the sun is also eccentric orbit. Okay, so when both these things reduce, effectively the ecliptic limit will reduce and it can come down to 15 degree 31 minutes. For lunar eclipse, it comes down to 9 degree 30 minutes. Under most favorable conditions, when the moon's size is larger, moon is at perigee, and also the sun's angle subtended at the moon's orbit, okay, or moon's orbit, that is going to be larger, we get more favorable conditions for eclipses, and ecliptic limit can go to something like 18 degree 21 minutes for solar eclipse and 12 degree 5 minutes for lunar eclipse. 12 degree 5 minutes for lunar eclipse multiplied by 2 on both sides, total distance is 24 degrees. Even that 24 degrees is smaller than the lunar month, and therefore even under favorable conditions it is not guaranteed that full moon will take place or the lunar eclipse will take place. Okay, so because the full moon might have happened just before the ecliptic limit started for the lunar eclipse, okay, and the next full moon will happen after this. So about full moon, about lunar eclipse, there is no guarantee. Okay, one needs to do calculation when exactly the sun is and whether the full moon is close to that. But about solar eclipse, we can always say that even under unfavorable condition, this multiplied by 2 will give you about 31 degrees. Okay, and the lunar month is 29.5 days, takes 29.5 days, and this is 31 degrees available. So we, even under unfavorable conditions, we know that solar eclipse will take place when the sun is near any of the nodes, and it will come near ascending node at one point of time, and after 6 months after 6 months to the other node, and therefore every year minimum 2 solar eclipses must happen. So now we look at the conditions for maximum duration of solar eclipse and so on. The moon should be nearest to the earth, so that is perigee. Here the maximum angular diameter of the moon is 33 arc minutes, 30 seconds. And this position comes every 21.5 days, because the moon is going to come near perigee every 27.5 days. But of course, on that day, it is not necessary that the new moon will take place. The sun should be farthest from the earth, aphelion position. Why? Because if sun is farthest, what will happen? Sun is going to be smaller in angular size, the moon is larger in angular size, and therefore solar eclipse will last for longer duration. So this position comes after every 365.26 degrees. Okay, that the earth is going to be at the perihelion position, at the aphelion position. When the moon is near zenith, it is nearer to the observer by radius of the earth. Okay, see, all calculations you have done with respect to the center of the earth, but moon comes on zenith, you are closer by 1 radius. So 1/68 of the distance you are improving. It means the improvement is more than 1%. Okay, and then hence the angular diameter of the moon is greater. So on the zenith, the actual angular diameter of the moon will be greater. We know the perception that when the moon is near horizon, it appears to be greater. But when you take a photograph, the instrument will tell you and make measurements. Okay, that will tell you that moon near zenith is actually larger. Consequently, the duration of the solar eclipse is also going to increase because of that. There are other parameters for maximum duration of solar eclipse, but 2 important parameters: that moon should be near perigee, okay, and wherever the eclipse is taking place, the moon should be near zenith. Then shadow of the moon should have minimum speed, because if the shadow, see what happens, as the moon is also going around the earth, the shadow of the moon is going to travel on the surface of the earth. Okay, and earth is also rotating, so therefore the surface of the earth is also moving. So if the surface of the earth is also going to move in the same direction as the shadow is going to move. However, shadow of the moon moves faster. Okay, so it is flight. But if you are located closer to the equator, naturally the surface of the earth is going to move faster. You know that because what is the actual velocity? What is the translational velocity? It is omega times r. So when r is largest, okay, that is near the equator. If you go to any particular latitude, any higher latitude, okay, effectively you are moving in a smaller circle, and then the velocity of the earth at that particular point is going to be smaller. So near equator, it is going to move Earth's surface is going to move fastest. The moon shadow typically moves with respect to Earth's center from west to east at a speed of 3,380 km per hour. At 40 degree latitude, if you take, the surface speed of the Earth is 1270 km per hour. And we are interested in this difference. If this difference is maximum, then eclipse will be visible for more duration because you will be there in the shadow for longer time. At equator, the surface speed is 1670 km per hour. So you see at 40 degree latitude, the surface of the Earth is moving relatively slowly. At equator, it is moving 1670 km per hour. If you go to 60 degree latitude, it will be moving half this. Okay, half this particular rate. Okay, but we are interested in the difference between the sun's the shadow speed and the speed of the Earth's surface. So the shadow speed with respect to Earth's surface is 1710 km per hour, and that will tell us how long the eclipse will take place. Okay, so let's come to the next point here. The next point is about the eclipse years. We already talked about that the eclipses take place in certain seasons. Okay, and the seasons seem to be shifting. So see here, the line of node at one particular point of time is along this direction, and say approximately 2 years later it is along this direction. So it is moving from as seen from the north, it will be moving in the clockwise direction. This is the retrograde motion because the orbit of the Earth, the rotation of the Earth, everything is anti-clockwise direction, whereas the line of node is moving in the opposite direction in anti-clockwise direction. Now duration between the two successive meeting of any nodes and the sun is called eclipse year. What does it mean? It means that if the apparent motion of the sun is like this, so sun comes near the node. After one revolution, again sun is going to come near the node, but by that time the node had shifted backwards, so it is going to meet the node earlier than 365 days, and that period is called eclipse year. So it is effectively a synodic period of the nodes. These nodes, ascending descending nodes, persist in retrograde fashion with a period of 18.61 years, and therefore it is smaller than the sidereal year. Okay, what is smaller than the sidereal year? Eclipse year is smaller than the sidereal year, and its magnitude, its duration is about 346.62 days. This is going to be useful for predicting for future eclipses. Okay, because eclipses are going to be decided where the sun is closer to the node, and node is preceding back. Therefore, next eclipse will come earlier. So, if last year eclipse happened say in December, this year it will happen in November. In fact, it is happening on 25th of October. Okay, next year it will happen even earlier because every year the node is going to shift backwards, and therefore sun is going to come closer to the node earlier and earlier. So eclipse seasons keep shifting in a backward direction. Let us come to an interesting calculation. How many minimum eclipses can happen in a year? And we already talked about that at least 2 solar eclipses will take place and no lunar eclipse may take place. So our answer is ready. So let's look at the argument. The ecliptic limit for solar eclipse on one side of the node is 16 degree 54 minutes. So total range is going to be double of that, 33 degree 48 minutes on an average. Angular distance traveled by the sun in one lunar month, okay, is 29 degree 6 minutes. Angular distance traveled by the sun per day is 59 minutes 08.19 pr/second per day, and then one lunar month is 29.53 days. So when you make this multiplication, you get the motion of the sun in one lunar month is 29 degree 6 minutes. This is surely smaller than this, and therefore near each node sun will always be inside the ecliptic limit during at least one new moon. It may happen that 2 new moons may take place. So the sun has entered ecliptic limit, new moon date took place, next lunar month is happening after 29 degree 6 minutes, and the ecliptic limit will end at 33 degree 48 minutes. So it is possible that there can be two solar eclipses around one particular node. You know, 2 consecutive months solar eclipse is there. That can happen. But we are talking about how many minimum eclipses are possible. So at least one has to be there. Sorry. In a solar year, therefore at least 2 solar eclipses happen, one near each node. The ecliptic limit for lunar eclipse, on one side we have calculated as 10 degree 50 minutes. Total range of ecliptic limit near any node is going to be 21 degrees, therefore 40 minutes, double of this on an average. Hence, it is not ensured that full moon will happen near every node, because sun will take 29 degree 6 minutes to go to the next full moon position. Okay, and by that time it would have left the ecliptic limit. Remember, when I am talking about the lunar eclipse, that time also I am talking about sun coming closer to the node. Because when sun is coming closer to, say, ascending node, the moon will be near the descending node. It is exactly 180 degrees and it is full moon day. So the longitude difference is 180 degrees. So I can always talk in terms of when the sun is going to come near the node, okay? Because moon keeps coming near the node every month. But that is not important. Sun also should come, and sun is going to come only twice a year. So we always talk about sun coming closer to the node. If full moon happens, surely it is going to be lunar eclipse. If new moon happens, surely it will be solar eclipse. In a solar year, minimum number of lunar eclipses therefore is 0. Minimum number is 0. It is not necessary that it will be always 0, but sometimes the lunar eclipse will take place, but it is not essential that it must take place. So you may find that there are certain apps which will give you the dates of eclipses, and I will show you one of the apps later in this lecture. Okay, that it is possible to have the minimum number of eclipses possible in a year, therefore is 2 solar eclipses, 0 lunar eclipses. That's the minimum. Now let us look at maximum eclipses in a year, and there is an interesting series of maximum eclipses. The node regresses about 19 degrees per year. Regresses means it moves in a retrograde fashion. Okay, so this is 19 degrees per year. Okay, so actually it is 1.56 degree per lunar month. Let me just make that correction. Sorry for that. Okay, sorry. I mean it is the same line because I have put another slide on this side. So node regresses 19.344 degree per year, which is 1.5 degree per lunar month, or 9.3 degree in 6 lunar months. Okay, after 6 months, the node has shifted 9 degree backwards. So 1 lunar month is 29.53 days. 12 lunar months is 354.4 days. You just multiply with 12. Keep correct number of significant digits. Now let us look at the case 1. We are looking at maximum eclipses in a year. The sun enters ecliptic limit at, say, first node. Okay, the first node could be anything, but let's suppose near the ascending node. Okay. Now day 1 of the year, sun is already inside the ecliptic limit. I have not mentioned when it came inside the ecliptic limit, but let us suppose day 1 of the year, the new moon day occurs, and then because sun is already in the ecliptic limit, solar eclipse will take place. We will call this as solar eclipse 1. After half month, full moon day will occur, and already sun is in the ecliptic limit, therefore lunar eclipse will take place. We will call that lunar eclipse 1. After 1 month, the sun has not yet gone out of ecliptic limit, and therefore whenever the new moon day is going to occur, second solar eclipse will happen in that year. See, within the first month of the year, 1 solar eclipse, 1 lunar eclipse, 1 solar eclipse is happening. Now sun is going to exit the ecliptic limit at node 1. Okay, you know how much time it takes to exit. Okay, about 33 days or so. Now Sun is going to enter the ecliptic limit at node 2. That is going to happen typically about after 5 months, 6 months. On the day 148, the new moon day is going to occur, and that will be called solar eclipse 3. This is after 5 months. On day 163, a full moon day will occur. How did I calculate this? Day 148, day 163? What you have to do is you have to multiply 29.53 with integer number. Multiply it with 5, multiply it with 5.5 for full moon day, and so on. Day 178, the new moon day again occurs, and solar eclipse will happen. See, this is going to be near the second node, and Sun is going to remain inside the ecliptic limit. The Sun is going to exit the ecliptic limit at node 2. Okay, so basically 3 eclipses here, 3 eclipses here has taken place, 6 eclipses have taken place. In a year, we know that Sun is going to come near each node once, but because node is going to precess back, 19 degree it is going to precess. Okay, the eclipse year will end at 346 days. 347th day of the year eclipse will end. The eclipse year will complete, which means Sun will again come to the first node. Within a same year, Sun is again coming to the first node. Node has regressed by 19.3 days or 19.63 days, and therefore on the day 355, after 12 months exactly, 12 lunar months. This was on day 1 plus 354 days. So on day 355, the Sun will be in the ecliptic limit again. And on the day 355, the new moon day will occur, and that is going to be the 5th solar eclipse in the year. So on the very first day, suppose new moon day occurs, okay, it is possible to have 7 eclipses in a year. That's the maximum possibility. So how many eclipses, solar eclipses? 1, 2, 3, 4, 5 solar eclipses, 2 lunar eclipses are possible. This is one kind of scenario where you can have maximum 7 eclipses with 5 solar, 2 lunar eclipses. There is also another scenario, we'll talk about that now. Is this slide visible and am I audible?
You are audible. Your slide is also visible.
Thank you. So maximum eclipses in a year, second case we are now talking about. So Sun enters the ecliptic limit at node 1, and instead of new moon day, the full moon day has occurred. So day 1, let us suppose is a full moon day and lunar eclipse 1 takes place. Day 15, Sun is still going to be inside the ecliptic limit. The new moon day has occurred and solar eclipses have happened. Now after another 15 days, the Sun would have left the ecliptic limit for lunar eclipse, because lunar eclipse ecliptic limit is smaller, and therefore on 30th day, though there will be full moon, there won't be any lunar eclipse. So Sun is going to exit ecliptic limit at some point of time. Okay, for next full moon day, the eclipse will not take place. Now Sun, after about 6 months, Sun is again going to enter the ecliptic limit at node 2, second node. On the day 163, the new moon solar eclipse, new moon day will happen and solar eclipse 2 will take place. So you have to count again from this, okay, 6 months, 6.5 months or 5.5 months. So basically after 5.5 months, you will get this much, these many number of days, okay. And then on day number 172, the full moon will take place, okay, and that is going to be second lunar eclipse. Then on another 15 days, day number 192, the new moon will take place and solar eclipse will take place. Now see what is happening here. The solar eclipse, lunar eclipse, solar eclipse pattern is repeated around that second node. Around the first node, the full moon was there, and the new moon was there. The second full moon was not possible. Okay, but new moon, full moon, new moon is going to be possible here. Now Sun will leave the ecliptic limit at node 2. But again, node has regressed by 19.63 days, and therefore on the day 340, the new moon solar eclipse will take place.
Google sheet
On the day 3:55, the full moon will be there and lunar eclipse will be taken. So now count how many eclipses are there in that particular year. We started with a full moon, lunar eclipse 1, then immediately there was solar eclipse. After 6 months, solar eclipse, lunar eclipse, solar eclipse took place. Okay, and before the end of the year, again at the first node, the solar eclipse and lunar eclipse are going to take place. So there will be basically 4 lunar eclipses and 3 solar eclipses. Okay, 4 lunar. This should be 4 solar eclipses and 3 lunar eclipses will take place. Lunar eclipse 1 at the first node, 1 lunar eclipse, 1 solar eclipse. At the second node, 2 solar eclipses, 1 lunar eclipse. And at the third node, again 1 solar eclipse, 1 lunar eclipse. So basically, 7 maximum eclipses can happen in a year. And we can see the dates if you look at the ephemeris, if you look at the tables of eclipses. One example is here. This is going to happen in 2028. But now it is not exactly one, I mean it is one calendar year, though the year number is not exactly same. 31st December 2028, first lunar eclipse takes place. 14 January 2029, first solar eclipse takes place. 12 June 29, solar eclipse, second solar eclipse takes place. Then 26th June, lunar eclipse takes place. 11th July, solar eclipse takes place. 5th December, solar eclipse takes place. 20th December, lunar eclipse takes place. So we have 3 lunar eclipses, 4 solar eclipses happening in 2028 to 2029, but within one calendar year. From 31st December to 30th December 29, within one calendar year, 7 eclipses are taking place. This had happened also in the year 2010 and 11. Okay, and we'll see that approximately after every 18 years or so, it is going to repeat. This kind of pattern may repeat. Not exactly, not precisely after every 18 years this will happen, but more or less between after 18-19 years this happens. Now there is a reason why it happens. So let's now come to the statistics of frequency of solar eclipses. So you have out of total 26.9 total solar eclipses at 26.9% are total solar eclipses. 33.1% is annular eclipse. We have already seen why this is so, because on an average the lunar diameter is smaller than the solar diameter, therefore there is more possibility of annular eclipse than total eclipse. So annular eclipse is more. Then also there are 4.8% possibility of this 4.8% possibilities of annular and or partial eclipses. Now what is meant by annular or partial eclipse? What happens is what happens is this, that I mean it is also called hybrid eclipse, is that near the globe of the earth. Let me just write on this, I can explain by drawing the diagram here. I hope you can see this diagram that I am drawing here. Can you see?
Yeah, it is seen. You can draw.
Yeah. Thank you. So, I mean, this is just I'm not very comfortable on a pen tab, but imagine this is the Earth, and the Moon is here, and the Moon is going to have a shadow. Okay, Moon shadow. If it doesn't reach the Earth completely, then it is annular eclipse. If it doesn't reach the Earth completely, it becomes annular eclipse. Now this is annular hybrid eclipse. That means it is annular and total. Okay, it shouldn't be partial. Annular total eclipse. So what is happening is this, that if the globe is like this on this side, okay, and when the shadow is here, it is not reaching. When the moon is here, when the moon is here, it is not reaching the shadow. But when the moon comes over here, it reaches the shadow. And when moon goes over here, again it doesn't reach the shadow. So moon is traveling, its shadow is moving, and because the curvature of the earth, only at certain locations the shadow is going to touch the surface. Those people will be able to see the total eclipse. Other people will be able to see the annular eclipse. So such kind of hybrid eclipses are possible. It is called hybrid eclipse. And there are about 5% eclipses are hybrid. So the 33% eclipses are annular, 26.9% eclipses are total, okay, out of these, and 35% eclipses are going to be partial eclipses. When does a partial eclipse take place? We are not talking about partial eclipse means, suppose now take example of 2034 from Srinagar you will be able to see total eclipse. Okay, but only from Srinagar you will be able to see total eclipse. If you come to Mumbai, if you come to Delhi, the eclipse will be partial. So I'm not talking about those partial eclipses. I'm talking about when I say partial eclipse over here, from any place on the earth, it is either partial or eclipse is not seen. This is what we mean by partial eclipse here. Okay, so 35% eclipses are partial means from no location on the earth they will be seen as total or annular. This typically happens when the shadow is falling near the North Pole or the South Pole. Near the poles, when the shadow falls, okay, you will not be able to see the total eclipse at all. Okay, shadow is just missing the North Pole or South Pole. Okay, and in those regions are still coming in the penumbral shadow, and penumbral shadow region means the people over there will be able to see the partial eclipse. So we can see that 35% of the eclipses are only partial. From no place on the earth they will be total, and remaining total or annular eclipses, these are called central eclipses. Okay, they are distributed like this. Ratio of annular to total eclipse is 5:4, and that is also the ratio of the average size of the sun to average size of the moon. The average solar eclipses per century are 237.8 eclipses. I mean, why this fraction is because over multiple centuries you may get 237 or 238 eclipses. Okay, and there's more probability of 238 eclipses. Some years you may have 237 eclipses, so the average becomes this. Maximum number of solar eclipses per year we have already seen is 5, and out of that 4 will be partial eclipse. Okay, so not all 5 are going to be total eclipse, the 4 will be partial. Minimum number of solar eclipses per year is going to be 2, and here it is both can be partial. Both can be partial here. Maximum number of total solar eclipses per year are 3. Minimum number of total solar eclipses per year can be 0. What does it mean? It means that 2 eclipses happen, both were partial. Okay, very unfortunate here that there will be no solar eclipse, no total solar eclipse. And ratio of solar eclipse to lunar eclipse, typically this ratio is that we talked about ratio of beta to alpha. Okay, and you can bring it down to closer numbers. Instead of 7:4, you will bring it down to 3:2. Okay, something around that. But it is, I mean, this ratio is not exactly 3:2. Okay, beta is to alpha is the correct way of writing more precise relations. Maximum number of solar plus lunar eclipses per year can be 7. So we already seen that it could be 4 plus 3, 4 solar, 3 lunar, or 5 solar, 2 lunar. Okay, both these cases we had discussed. A small kind of a break about actual observations. Okay, some of the photographs I will share, and some of the activities I will discuss here. Some of the activities that my college students group we had conducted along with our Mumbai University astronomy course. So this is a simple photograph, photograph of this annular solar eclipse. We had gone to Mangalore, so this is that annular solar eclipse photograph. Now for total solar eclipse, naturally you will see corona and other effects, but for annular solar eclipse you don't see anything. You put filter on the camera and you take photograph. Okay, because without filter it is not advisable to see annular eclipse. However small this limb of the sun is seen, it is still very bright and it is going to have a focused image on the retina and it is going to burn the retina. So there are two kinds of problems. One is the brightness of the limb is still very high, and when that is going to get focused on the retina, it can easily burn the retina. Second problem is because major part of the sun is going to be blocked by the moon, the effective intensity will reduce by large amount. And when the effective intensity reduces by large amount, with our natural reflexes, our pupils get dilated, okay, so that more light can come in, and that can further damage the retina. Also, what damages retina more is the infrared radiations, okay, so which you can't otherwise also see. It is the visible part of the light, okay, that may brighten your eye and that may have a reflex to close your eye, but the infrared can still keep, infrared can come if you don't close the eye. Infrared is more in amount as compared to visible light, because visible light, if you consider, is about 40% of the total amount of light that we are getting from sun, okay. Larger amount is infrared radiation, and therefore that can really damage. But this is an interesting photograph with a camera attached to telescope taken, or directly using camera also you can take. One simple way of observing is you project the image of the eclipse on the screen and you can watch that. You can put filters in the binoculars. So there are filters available on the binocular and you can watch through that. These are all our student volunteers. You can apply a simple, this is a very amateur telescope, 5-inch Newtonian telescope, and there is generally a hole given to put a solar filter. So you put the cap on the telescope and then you put a solar filter because there is, on the cap opening is given, so you can attach solar filter. You need to be specially careful because solar filter, even though it is fitting nicely, okay, sometimes what can happen is because of the wind or because of the somebody becomes careless and it may just fall off, and if imagine a person is watching, he will be able to see the entire sun, okay, entire bright sun, and surely will damage his eyes permanently. So you need to take some special precautions, okay. Extra precautions are always useful. You may photograph using filter on the camera. So again, here the filter is put on the camera and camera is mounted on the tripod, and you've done this. You can take photograph. You need to do preparations. Well, so when this eclipse was on 26th December, we had gone day before. In fact, we had reached there on 24th December. 25th December, during eclipse period, it was 8 to 11 in the morning. During eclipse period, we had set up all the instruments to check where the sun will be coming, at what angle sun will be coming, will you be able to focus correctly, what angle you should be keeping. You get some practice, okay, on a day or I would say day -1, okay. An earlier day. Also many times what happens, this is not our regular place. I mean, we are living in Mumbai, we have gone to Mangalore for this eclipse. Okay, it becomes useful to get used to that particular place, because we don't know many times, we had planned a proper hotel where we could get this view in near the sea, but even then you don't understand many times local conditions. So go one day before, see what is happening, see whether some kind of wire is obstructing in between, because there could be different kind of cables running from one tree to another tree or places, and it may happen that in that from 8 to 11, whatever is the path of the sun, okay, that may cross that particular some cable or wire in the air. So you may have to avoid that place, because or at least you need to find out exactly what time it is going to get obstructed, and will remain there for a few minutes, okay, because sun takes about 2 minutes to travel vertically away from the horizon, but if it is moving at an angle, it may take slightly more than 2 minutes. So you need to bother about that part. Or you can just wear solar goggles and enjoy the eclipse. Okay, various ways you can do this, but you can be more serious and decide talk about projects like Ganguly sir mentioned about the different kind of projects that we done. The simplest kind of project that you do is this. This was done at the annular eclipse of 2010, 15 January. We had not gone to Kanyakumari. It was visual from there, but this was taken in Mumbai in my college itself. So you have to take simple view, and you can see that it acts as a pinhole camera. So every hole you can make out the image of the sun is there in the eclipse. So through every hole you get an eclipse. You can simply make a small pinhole with your fingers, and this is the picture taken on 21st of June this year, 2021. Where the eclipse was there in June. Due to pandemic, we couldn't go anywhere, and so I decided in my building itself, I will make observations. So with the hand, you make a pinhole, and you can nicely see over here the crescent of the sun. Okay, when it is obstructed by the moon. The gaps in the leaves can, okay, so you need to be visible and find out gaps in the leaves can act as a pinhole camera, and this is how we can go and take pictures. So photography can be one very interesting area, and nowadays every mobile has camera, but if you have DSLR camera, it really helps. So you can take photographs like that. If you are prepared, clouds may also serve as filter for camera. So this was photograph directly taken without any camera on that 21st of June, and it was cloudy. It was June, it was cloudy, and we could get a nice picture of this eclipse over. Okay, so it is possible that once you are prepared to do, okay, you can tap many different kind of methods to do things. Now, this was done again at Mangalore last year. That because we had gone, we say that let us see whether limb darkening effect can be seen. And what was done was very simple thing. This is not a telescope. This is just a simple pipe. At the front top, simple pipe, simple tube. Okay, at the front top, we had put a small hole. So that created an image of the sun, like pinhole image. At the center over here, a small photodiode is kept. You may keep even LDR, and you don't have to do anything. You don't have to move telescope. You don't have, or this particular tube. You just keep the tube there. Okay. As the sun is going to change its position, this disk will slowly shift over your photo detector. What will happen? When the limb of the sun is falling on the photo detector, you will get certain amount of intensity that you can measure using electronic devices. As the sun is going to shift, the center of the sun will come. That will give you different kind of intensity. And again further, when the sun shifts, the end of the sun will again come on the photo detector. That will give you a different intensity. What is observed is sorry, near the limb of the sun, the intensity is less. Near the center of the sun, the intensity is large, and it is called limb darkening effect. It's a very prominent effect, and a simple device like this can be used. Okay, this device was, we have taken help of Dr. Vinita Navalkar, who is an astrophysicist, and she was my student. So she helped us design these ideas and these instruments, and we developed this. Unfortunately, she couldn't come for Eclipse, but our team worked with her help to do these kind of measurements. These were the data that was taken. This is the observed data. This data was taken on 27th, okay, day after eclipse. This data was taken during the eclipse. Okay, so we'll see what happens. This is the time duration. Okay, the intensity increased first, then it decreased, then again it started increasing, and you can see that on the next day, when the eclipse was not there, the intensity from 8 o'clock to 11 o'clock went on increasing. Why the intensity went on increasing? It went on increasing because of two reasons. One is, as the sun is going to increase its altitude, okay, it is going to, the sun rays are going to come through thickness of atmosphere. Okay, so what we call the See, as the zenith angle reduces, the intensity goes on increasing. Okay, because the what we call zenith extinction is also applicable for the sun. Okay, so as the time increases from 8 a.m. to 11 a.m., the intensity would have increased. Now here intensity initially increased before the eclipse. When the eclipse started, intensity started falling, and then again it started increasing, and it is not symmetric because there are three kinds of effects which are happening here. Those three kinds of effects are, as the altitude of the sun is changing, the intensity should increase. As more and more part of the sun is going to get obstructed, as the moon is going to cover it, the intensity should fall. So this is another second effect. Third thing is, as the moon is first going to obstruct only the limb, and limb is not very bright, okay, the intensity fall will not be much. But at the center, the brightness is very high for the sun, and when the moon is going to block that, the intensity is going to fall more. So there are three different effects. One is, as the altitude changes, intensity is going to increase. As moon is slowly going to cover the sun, one circle is covering the other circle, okay, the exposed area of the sun is going to go on reducing and then again go on increasing. And then you also need to consider the weighted average of each of those pixels, because at the center the sun is brighter, near the limb it is faint. When you do all these three things together, this was what was the modeled graph, and you can see this modeled graph nicely matches with this graph, and this was purely done on Excel. So using Excel you can do this. Such kind of experiments can be done, and for whichever next eclipse possible, you may try out doing these things. You may also do these things for lunar eclipses, where lunar eclipse things are going to be different, but basically you won't have limb darkening kind of effect, but you can always see the altitude effect, and you can always see how the intensity changes. You will also have additional effect that when moon enters the earth's shadow, okay, the central region of the shadow, it is quite dark. The external region of the shadow is not very dark, because due to refraction some amount of light does reach over there. Okay, so one can do such kind of experiments, and there was no manipulation over here. I mean, I'm saying that why that you only had to do the data fitting. Okay, these were arbitrary units, and using arbitrary units, however, you see the profile nicely matching correctly. So such kind of experiments can be done. The ecliptic coordinate system slide actually not required over here, but this is basically to talk about the latitude longitude effects. And the latitude, when do we say that it is full moon? So basically we are talking about the celestial longitude. We always measure the celestial longitude, the coordinate along the ecliptic. Okay, and even if moon is making 5-degree angle, moon's plane is making 5-degree angle, you take a projection on the ecliptic and measure the longitude, and there are all ephemeris. Why only ephemeris? Even the panchangs which are available, the local panchangs which are available, okay, give you one particular the celestial longitude. Okay, so celestial longitude is easily available in ephemeris as well as panchangs for sun and moon, and one can do calculations using those, that how much is the motion of the sun every day, how much is the motion of the moon every day. Okay, and these kind of calculations become useful when you are doing eclipse related calculations. There are 5 types of months. Out of 3 different types of months are going to be useful, because I'm going to talk about an interesting phenomenon called Saros cycle. So what are the 5 different types of months? They are all related to moon, of course. The motion of the moon, the orbit of the moon with respect to sun. So when it comes in front of sun, and again when it comes after in front of sun, it takes 29.53 days. That duration is called synodic month, which is typically what we call lunar month. Sun will cross the moon will, as it's going in the orbit around the earth, okay, on the ecliptic, or we can take its direction along the ecliptic, we can measure its longitude along the ecliptic. The moon can cross over the vernal equinox, and again it can come back to vernal equinox. But during this one period, the vernal equinox would have slightly shifted in the backward direction, and therefore this duration is smaller than the actual period of rotation. The actual period of rotation of the moon around the earth is given in terms of with respect to stars. Okay, why I am saying actual? It is in the inertial frame of reference that we are talking about. So with respect to stars, the period of revolution of the moon around the earth is 27.321662 days. And with respect to vernal equinox, it is slightly smaller because during 1 month or one particular revolution around the earth, vernal equinox would have slightly shifted in a backward direction. However, this tropical month is not a very useful concept. Tropical year becomes useful when we talk about the sun crossing the vernal equinox and again next time crossing the vernal equinox. That is called tropical year. But tropical month is just a concept. It is not generally very, very useful. Anomalistic month becomes very useful concept. Perigee to perigee motion. During the motion of the moon around the earth, the perigee advances in the same sense, and therefore suppose the moon was on perigee at one particular point, after one complete revolution, okay, in the inertial frame, it will not exactly come again on the perigee because perigee would have slightly advanced, and therefore to come on the perigee it will take extra time, slightly more amount of time, and therefore this particular month, the anomalistic month, is 27.5545 instead of 27.3216. And the fifth kind of month, again it is very useful when it comes to calculation of eclipses, is called draconic or nautical month, and the reference point is ascending node. So if moon crosses the ascending node, after how much time again it will cross the ascending node? Now typically it should be one particular orbit around the earth, 27.32 days, but during this time the vernal equinox, the ascending node itself would have slightly shifted in a backward direction because ascending node is precessing in backward direction, and therefore the moon next time will reach ascending node slightly earlier. Instead of 27.3216 days, it will reach 27.2122 days. Okay, it will be earlier. So the useful concepts here are sidereal. This is the motion of the moon with respect to inertial frame. During that time, Earth is going to move in the orbit of the sun, and therefore moon will have to catch up if it has to again have new moon day or a full moon day. Okay, so synodic month is 29.53 days. This we had seen right in the beginning of this lecture. Moon's position with respect to its perigee becomes useful, but perigee advances, so this anomalistic month is slightly greater than sidereal month. Moon's motion with respect to ascending node is also important, but ascending node regresses in a backward direction, retrograde fashion. Therefore, this nautical month is smaller than the sidereal month, okay, by a small fraction, and we'll see how this becomes useful when we talk about the other. There is an interesting concept called Saros cycle. What is the Saros cycle? It has been observed that eclipses surely repeat after a period of about 18 years and 11 days. So this cycle is called Saros cycle. The lunar orbit makes an angle of about 5.1 degrees with the ecliptic. We have seen this. The lunar orbit intersects the ecliptic in 2 points, ascending node and descending node, and it precesses due to sun's gravity. So this ascending descending node slowly turns in backward direction. It takes around 6798.38 days or 18.6 years for the ascending or descending nodes to come back to the original position. And when that happens, okay, there is going to be a tendency that the similar kind of eclipse cycle will repeat. But it is not exactly 18.6 years. So let us see what all coincidences have happened. Okay, Saros cycle is the effect of certain coincidences. Let us see. As the moon moves on the ecliptic, okay, we are talking about moon moving means with respect to Earth. It crosses the ascending descending node. Once cross the ascending node, it will cross again after 346.62 days, which we have already called as eclipse year. Okay, so remember this figure of eclipse year, 346.62 days. Remember also the tropical year, 365.2422 days. And also you can remember that 12 lunar months is going to be 354 days. So there are different durations here. Okay, the eclipse year is going to be different, tropical year is going to be different, and 12 lunar months is going to be different period. Okay, they are going to be comparable but not exactly same. So now, one eclipse year is 346.62 days. So if you consider 19 eclipse years, multiply this with 19, you get 6,585.78 days. I have purposely written this fraction because this is going to be useful. The synodic month we know is 29.53 days. I have written extra significant digits here. This is month with respect to sun. And you take 223 synodic months, that gives you again 6585.32 days, slightly different than this. So 6585.32 days is basically 18 years, 11.3 days or 10.3 days if there are 5 leap years within this particular period. This particular period is called Saros. So after every 223 synodic months, there are going to be 19 eclipse years completed, and therefore the sun is again going to come. Suppose here the sun was near the one particular node. After 223 synodic months, again it is going to come near the node because it would have completed 19 eclipse years. So see, there are two factors coming over here. If the solar eclipse has taken place, it implies two things. One, it implies that it was a new moon day. Second, it implies that sun was near the node. After 223 synodic months, again it is going to be new moon day. But that much period is 6,585 days. That also matches with 19 eclipse years, means sun is again going to be near the node. So both the things are going to match, which ensures that surely after 19 eclipse years or this 18 year and 11 days, again solar eclipse must take place. So this is giving you a guarantee that if there is a solar eclipse, after 18 year 11.3 days, again there will be solar eclipse, 100%. 100% surety that there will be solar eclipse. The fraction of 3.32 days over here is about 1/3 day. What it means is that the instant of new moon is going to get shifted by 0.32 days or about 8 hours. So if the solar eclipse is visible over here at some particular time, okay, after 18 year and 11 days, it will be visible after 1/3 of a day, which means to 120 degree western longitude. So eclipse in the Saros cycle is going to shift to the west. So the eclipse will be seen not in the same place, but there will be an eclipse which will be shifted to 120 degree west region. This is a graph. This is the plots of all those different eclipses, which are all belong to one particular Saros cycle. The Saros cycle is numbered as 136. I will mention what is this 136 number. So consider the eclipse which took place on 18th May 1901. The next, after 18 years, it was in 1919, 29th May, and it was visible over here. Now this was an important eclipse which was also used by the Eddington's team. Okay, and then another 18 years rather, the eclipse took place here. See that it is shifting by 120 degree towards the west. The next eclipse again shifted 120 degree towards west, and it is in 1955. Next one was 1973. Next one was 1991. Next one was 2009. Next one was 2027. Again 2045. It is going to be there. Okay, so it is shifting every 18 years. Surely there is an eclipse, and it is shifting to the west. Also, you will see that it is shifting towards north slightly. So here, this is one eclipse. This is slightly towards north. This is slightly towards north. This is slightly further north, further north, further north, and so on. So ultimately, it is going from here to here or here to here. Okay. So it is not only shifting to the west; it is also shifting to the north. Now I mentioned here there will be eclipse which could be shifting to the south also. So in the next slide, we will see when that happens. So first we are talking about magnitude change. What is magnitude? The eclipse magnitude is the ratio of sun's disk to the moon's disk. or rather moon's disk to the sun's disk. So eclipse magnitude, if moon's disk is smaller and sun's disk is larger, is going to be less than 1. If sun's disk is smaller and moon's disk is larger, eclipse magnitude will be more than 1. Anomalistic month will decide the size of the moon's disk, because anomalistic month is related to perigee or apogee. E is 27.55 days. 239 anomalistic months give you again similar figure, 6585 days. But now here the fraction is 0.53. This period is slightly greater than 223 synodic months, which is 6585.32. So if during one eclipse if the moon is near perigee, the next time it will lag behind, because it will come on the perigee after 0.53 days, whereas the new moon instant has occurred at 0.32 days. So what would happen? Right now the moon's, suppose that the first eclipse the moon's size was maximum, the eclipse magnitude was large. Next time it will slightly reduce, because moon size will become slightly less. Moon has not yet reached perigee. If initially therefore the eclipse is annular, it can become total. If initially it is total, it can become annular. Okay, if the moon was near apogee, next time it will be slightly short of apogee. At apogee surely it will be annular eclipse, and next time it will be before apogee, and therefore the moon size will be slightly larger, and there is a possibility that it can be total eclipse. Eclipse also shifts south or north, and that is related to draconic month. What is draconic month? Motion related to ascending descending node. So one draconic month is 27.2122 days. 242 draconic months will be again 6585.35 days. Remember, it was 32 days for synodic 223 synodic month. So the 223 synodic months were 1 Saros, okay, and it is slightly greater by 51 minutes. So everything is slightly greater. Instead of 0.32, you have 0.35 days. What does it mean? Every successive eclipse, the moon will reach node slightly later. So if eclipse has taken place near ascending node, the successive eclipse, the shadow will shift to the south. Why it will shift to the south? Because it has not yet reached the ascending node. So if it has not yet reached the moon has not yet reached the ascending node at the next instant, next Saro, okay, it means it is still below south, below equator or south of equator. So if moon is south of equator, its shadow will further go south. Okay, if moon is north of equator, not equator, the ecliptic, okay, its shadow will further go north. So if it is on ecliptic, the shadow will fall on ecliptic. So this is because at the time of eclipse, it has yet to reach the same position with respect to node. Hence, it will remain more south, and the shadow will be to the south. So if the eclipse can happen near ascending node, and the Saro cycle, whenever eclipses, when the sun is near ascending node, is odd number. So that Saro 136 implies that eclipse was happening near descending node. The number of solar eclipses in one Saro cycle are about 70 to 85. Okay, that means every 18 year the eclipse is going to take place. But we already seen that the eclipse goes on shifting either to the north or to the south. So if it is shifting to the north, what will happen? A point will come when the eclipse will go beyond the North Pole. At some point in the past, it might have started near the South Pole, and it is shifting to the north, and it will ultimately go beyond the North Pole. Similarly, if near descending node, the opposite thing will happen. Okay, and the eclipse will keep shifting in the opposite direction. Duration of one Saro cycle, okay, that 18 years, 11 days multiplied by these numbers can go to 1,200 or 15,000, 1,400, 1,514 years, okay, or 1,244 years. It can be this big, okay. So on an average, 1,300 years, one Saro cycle continues. So all the eclipses will have certain features, and they will progress in a particular direction. Number of Saro cycle at the same time are about 42. What does it mean? It means we say that there are 7 eclipses can happen in a year, or 5 eclipses can happen in a year. Okay, all those 5 eclipses naturally are going to be from different Saro cycles. A particular eclipse in the same Saros cycle will repeat only after 18 years. So all other eclipses which are happening, they are all part of different Saros cycles, and there are different Saros cycles for solar eclipse and lunar eclipse. Okay, so we are talking about solar eclipse. So total number of Saros cycles acting at a given time is 42 Saros cycles. If the Saros cycle, the first eclipse is partial, the next version ecliptic magnitude goes on increasing, then chain of total annular eclipses start. Finally, again the ecliptic magnitude goes on decreasing, okay, and ultimately you will have partial eclipse. Quickly, we'll talk about transits. There is an interesting mathematics of transit, but transit phenomena is relatively rare to be seen. Venus transit is almost not possible now because it happened in 2004. Fortunately, we could see it from my college. I could set up a telescope and show that. 2012, we were very fortunate that we could have seen 2004 and 2012 transits, but 2012 transit was not. It was completely cloudy and we missed that. Though we had prepared everything, we missed that. So some of these events are chance events and we take things. So here for Venus transit, there is an interesting cycle, okay, that goes that every 8 years, if the transit happens, that means the Venus passes on the surface of the Sun. Again, after 8 years, that can happen, okay, but then there will be a gap of 105 years, okay, and again after 8 years it will happen, and then there will be gap of 121 years. So there is a gap of 105.5 years. That means instead of June, it will happen in November, okay, or December, and then again there will be gap of 8 years, and again a huge big gap of 121 years. So total 243 years. Within 243 years, the cycle repeats. Okay, so it is like 8 year, 105.5 year, again 8 year, 121.5 year, and then the entire cycle repeats. So next Venus transit possible is in 2117 December 11. We don't know how much medical science will progress to keep us alive by that time. Why it shifts like that? So can be seen over here that Venus is seen over here, Earth is seen over here, and this is the transit location. Okay, after certain duration, you see the Venus would have shifted by larger angle, moved by larger angle. Earth would have moved by smaller angle. Okay, and when this repeats, after 8 years, the things are repeated. Earlier it was here, now it is along this line. So things are repeated but slightly shifted, and this is what happens again every time after 8 years or so. It has further shifted. Now there is, like ecliptic limit for solar eclipse, there will be ecliptic limit for the transit to happen, and therefore after 8 years gap you may see 2 transits, but again after 8 years the transit will be not seen because it will be beyond that ecliptic limit. Okay, so the logic remains similar, and using the actual data, one can do these calculations of how much it will get shifted, what is the ecliptic limit for Venus, and so on. And then the similar kind of patterns you can draw. Okay, and you can see here, this is a photograph, this is a small image or small video of Venus transiting over the Sun. But Mercury transits are relatively more frequent, okay, and their interval is 6 years, 7 years, 13 years, then 33 years, 46 years. There is mainly a cycle of 46 years, okay, but this can happen after certain number of years. Now, let me show you. This was a photograph taken by again my team. Okay, so you can see the small Mercury. This was taken on 2016 Mercury transit, and you can see a small Mercury over here, and you see its size is quite smaller as compared to the size of a sunspot over here. Okay, so sunspots are even much larger surface features on the Sun as compared to our planets. These are some of the dates. And the interesting dates, this is what we observed. The interesting date is now in 2032 and 2039, and one has to see from which location these will be possible. And I'm just showing a photograph. As I mentioned, I will share the greater documentation on the WhatsApp group from my friend Mr. Shishir Deshmukh, who actually does the occultation observations, plan things, do calculations. So his documents I will share later. But this was one random amateur photograph I had taken. Aldebaran occultation. Occultation is when larger body comes in front of smaller body. So you see here, this star is, this small dot is Aldebaran, and here is the moon. Okay, and this photograph was taken at 8:33 in the evening, and then at 9:11 on the same day, you see here a very small dot coming slightly below the moon. Okay, so the Aldebaran was behind the moon for that much duration, 8:33 to 9:11. So such kind of, I mean, if you know that such kind of occultation is going to be there, typically for the stars around the ecliptic, this can happen. And if you know that, you can always capture that in your photographs. If not, if you are not planned for more serious observations. So I stop at this point, and I will suggest you to use one particular app called Eclipse 2.0. Okay, it is available in the Play Store, and that app can give you from your location which all eclipses will be possible in the future or in the past, from the year 1900 to year 2100. Okay, so I stop at this point.
Thank you, my Shetty sir. If any participant